Okay, so just several remarks. So I hope everyone already see the announcement already. So just another reminder that final exam will be on next Tuesday, and so I will release at 12:45 p.m. And it's going to be in total 130 minutes, which means it's 105 minutes of exam plus 25 minutes of scanning. So you should be able to more or less finish the problem, like writing the problem around 105 minutes, at most 110, then that should give you enough time to upload and scan everything. So you may want to keep in mind that because this is final exam, right? So there will be a little bit more problems, which means that there will be a bit more papers that you need to scan, right? So so you definitely want to leave yourself a little bit more time than the exam one, exam two, right? So that's the thing you want to keep in mind. And also the review notes that I'm going to use for today, it's already posted, but I haven't posted the detailed solution. I leave essentially the solution to be blank for you to be able to like practice yourself, right? So so basically after today's review, not only I will post the notes, the thing I write today, but on the other hand, I will also post the detailed solution just in case that it's very likely that probably like I'm not going to be able to go over every single thing in the notes I posted because the time constraint today. So if it turns out that didn't cover maybe one or two problems, then at least you will have the detailed solution that I will post it. Okay. And also that I will announce later on, like later this week or over the weekend about the office hour next week. So I should have at least 1 hour to 1.5 hour office hour next Monday. So if you still have questions regarding the exam, you can definitely stop by. And no matter what, if you have any like question, you realize that you cannot stop by the office hour or you're not sure whether you can make it to the office hour next week, just feel free to email me over the weekend so I can answer the question. Or if you want, you can make an appointment with me. And don't forget the homework 11 is due this Friday. So I think after today's review, some of the questions should help you on working on the homework as well, if you still have last minute questions. Okay, so what I'm going to do today is I'm going to go back to start from chapter 4, because as I said, I'm going to the final exam will be focused on the new material. So I definitely will not be able to do every single thing in that we cover in this semester, but rather I'm going to point out several important things among chapter 4 and 5. And then also I will do, don't forget that the new material also including the 3.6. So I will also do some problem from 6.3, and depends on how much time we left, like we can do a little bit more if we still have time. So the main thing for chapter 4, as you already knew by now, that it's about linear transformation and also to find the matrix representation for the linear transformation. And also, don't forget, we talked about, we introduced this new concept, which is kernel and the range. So I kind of put all this concept together, right? So first of all, you should know how to check whether a map is linear transformation. So I'm just recall the definition here. So you have a map from V to W, which is a linear transformation, means that if you plug in the linear combination alpha V1 plus beta V2, then you can separate this linear combination. And this should be true for any vectors V1 and V2 come from the vector space, and also for any real number alpha and beta. Right, so this is similar to what you saw in chapter 3 when we check vector space, right? When you're trying to say something is true, you want to check like it's true for general situation, right? But if you want to disapprove something, you could just find me a counter example. Okay, so you want to be careful of the logic here. So the first example, let's take a look here. So I kind of put it in a bundle of like 4 parts of questions. So first I have this map, and I will tell you, actually, I didn't say that here, but I just say this is a linear transformation from R3 to R2, right? And the definition is given here. And part A, find the standard matrix representations of this linear transformation, right? And when I say standard, it basically means that it's with respect to the standard basis, right? So we are in R3 and R2, right? The domain is R3 and the image is R2. So standard basis is really just the standard one, you know, like E1, E2, E3, or E1, E2. So here, before we even start looking for the matrix representation, because we know it's the domain is R3 and it maps to R2. So right away, you should know that like the matrix representation you're going to find should be 2 by 3, right? First, you should have this in mind. So later on, when you find the matrix, you know that it fits the size here, right? So basically, we know back then that for standard matrix representation, that's the kind of the easy situation because we don't need to do any change of coordinate. But no matter what, you still need to plug in the basis into your transformation. So we know that the matrix representation we're looking for, the formula pretty much looks like this. So you plug in, okay, so first of all, the domain is R3, right? So you have the basis E1, E2, and E3, right? So that's the 3 vectors that we're going to plug in. So you plug in L of E1 and you have L of E2 and L of E3. That would be what this looks like for your matrix, standard matrix representation, right? So basically, then we really just need to find out all these 3 columns here. So L of E1 is really just L of 1, 0, 0, right? So here, be careful that we do this compact notation for the linear transformation, right? So L of X here, what it really meant is you plug in L of X1, X2, and X3, right? So you want to be careful the notation that what it really meant, right? Because a lot of time we write it in a compact way. So that's why you need to really pay attention to where the domain is in particular, right? Otherwise, you don't know, are you plugging 2 entries or 3 entries, right? So 1, 0, 0, so based on the definition of this linear transformation here, so you want the first coordinate is x1 plus x2. So the first coordinate plus second. And the second part would be x1 minus x3. So you use the first coordinate, subtract the third one. So you will get 1, 1, right, for the first column. And do the same thing for L of E2, right? So L of E2 is you plug in 0, 1, 0 into your map, right? So and then use the definition again. So you take the first coordinate, add the second, and first coordinate, subtract the third one, right? So you get 1, 0 as a second column. And then last one would be L of E3, which is L of 0, 0, 1. So it will be first plus second, first minus third. So this would be 0 minus 1. Okay. So you can see that it makes sense to see 3 columns and each of them with 2 coordinates, right? Because you're mapping into R2. So, right, so you should only see 2 coordinates as an image, right? If you see more than 2 coordinates, then something is wrong. So basically, you're plugging back all your information here. So this first column will be 1, 1, 1, 0, and 0 minus 1. So this would be your standard matrix representation, right? And so this is my A, right? So if you want to check your answer, right? So and then you can see that this is indeed 2 by 3, right? So this actually fits our expectation. And basically, you should check your solution, right? One thing you can check at this point is definitely that, so what's this A for, right? So this really means that if you have this linear transformation, right, it should really equals to A, this matrix A you just found, times X, right? Or you more precisely, L of X1, X2, X3 should really looks like A times X1, X2, X3. You should really check that this is true, right? That's where you want to check. Check that once you take A times X, it really fits the definition that we have here. That's the whole point. We want to find the matrix representation, because then you essentially turn a map into like some matrix A times X, right? So anything regarding the computation or the property of the map reduced to the property of the matrix in some sense, right? So then we later on, from now on in part B and C and D, you will see that then essentially when I ask certain question, then I'm looking for a certain space related to the matrix A. Okay, so any question for this one? It shouldn't be too bad. Okay, so now second part, I said, okay, so I mean, I'm using this example along the other 4 parts here. So I'm saying find the kernel and the range of this linear transformation, right? So first, let's recall what kernel means, right? So kernel, the definition, right? We usually use this notation, KER of L. So the kernel is really nothing else, but you collect all the vector from the domain. In this case, it's R3, such that when you plug in into L, the output is 0, right? So this is the definition of kernel of a linear transformation. But you can see that since from part A, we already know we can actually find or we already found the matrix representation, right? L of X. So basically, this is equivalent to solve L of X equals 0, but this is actually A times X, right? So you actually realize that all the solution X that you're looking for here, such that L of X equals 0, is nothing else. But yeah, it's actually not similar. So the kernel actually is exactly the same as null space for the matrix. So we kind of use the different terminology, right? So we usually say the vector that maps to 0 for a map, we call it kernel. And if it's any vectors that after A times X equals 0, we call it null space of A because it's essentially null space for a matrix. But it turns out that in this case, the kernel of L is exactly the same as null space of matrix A, if you can find the matrix A in part A, right? So if you still remember when you do the homework in section 4.1, because it's before 4.2, so we haven't really been able to solve the matrix A. So we really need to have to really write down what the map looks like and then maybe set up some equation. But once you know that technically L of X is really exactly A times X, you can reduce the problem to something really new, right? So technically in this case, we know once we found the matrix A, the kernel of L is equal to the null space of the standard matrix representation you found. So you need to kind of realize that there's the same thing. Then it's actually easier in the sense that we already know how to find null space of A, right? Back in chapter 3. So yeah, so then we can actually really solve for the null space explicitly. So let me check the matrix here. So it's where's my matrix? 1, 1, 1, 0, 0 minus 1. So I'm solving 1, 1, 1, 0, 0 minus 1. So I'm solving for the null space. Okay. So now I turn to solving the null space, right? So this is, okay, so I have a pivot here. So I'm just cancel out this. So I have 1, 0, 1 minus 1, 0 minus 1. Okay, so I want to just turn it into the REF. So eventually, I skip a little bit step here. You should actually write down step by step, but I want to speed up a little bit so you can actually get the REF like this. So this is REF. Right, technically you can start solving right at a certain point, but I just want to make sure we have all the information here. So now let's see. So okay, so we have REF, right? So then I have 2 pivots here. Okay, so now let's see. Okay, so REF. So this is x3 equals alpha, and x2 will be minus x3, which is minus alpha, and x1 is x3, which is alpha. So my solution would be alpha minus alpha and alpha, which is alpha times 1 minus 1 and 1, right? So basically, there's several ways you can represent this space, right? So I can say my kernel of L, which is essentially the same as null space of the matrix here. I can say that it's actually the span of this one vector, right? So it would be the span of 1 minus 1 and 1. Or depends on what the question is asking, right? Say if the question is asking for the basis for the kernel, right? So then you can say the basis of this space is just this one vector. Okay, so you can see that the reason I want to put this problem after finding the matrix representation is that essentially you should take the advantage of the matrix representation you just found. So whenever you see some kind of part of the question, you should think about that whether you can actually use some of the information from the earlier part. Okay, so I need a little bit more space for the part B for the range. So let me push a little bit down here. A little bit more. So now I need to find the range. Okay, so now let's see. So this is the second part here. So range of L, right? So what's range of L? right? So range of L basically means that you want to see the image of L after you're plugging everything in the domain. So to be more precise, range of L is really, you want to see what's all the possible output looks like, right? So basically, like sometimes you will see that people use this notation. So you want to collect all the vector as the output, right? So all the vector in the output, that means all the vector in R2, such that this vector comes from L of X. So you want to collect all the possible output, right? So whatever you're plugging in from X3, right? I don't know, like say 1, 2, and 3, right? You're plugging into L, you want to collect all the possible output, right? But if you think about it again, because we are using L of X, this should be able to be related to the matrix A, right? So just let me rephrase this. So you're collecting all the Y, right? I just rewrite L of X in terms of A times X. So this Y would be A times X for some X from the domain, right? If you remember that this definition, this is really nothing else but the range of my matrix, right? And if you still remember what range of the matrix is equivalent to, this is really nothing else but the column space of A, right? So let me remind you why this is the case, right? If you can reduce Y equals L of X into Y equals AX, right? Because we already found this matrix A, then you are essentially looking for all the possible linear combination for the column vector, right? Because A times X can be written as the linear combination of the column, right? So I'm looking for all the possible linear combination of my column vectors of A, which is really just the definition of column space of A. So you can see that now this is another example that why we are so happy to find a matrix representation, or maybe why people care about this matrix A, because now you really turn a problem of a linear transformation, like linear map, into something related to the matrix. And we know how to work with the matrix, right? So now essentially, long and short, we are looking for the column space of A, right? So again, there are several ways to write down your column space, right? You can tell me it's a span of something, or you can tell me its basis. But you probably already noticed that to find the column space of A, let's say we want to find the basis, but we already kind of do the REF like reduction, right? In this part when we're trying to find the kernel, right? So basically we already know explicitly when you do the like Gauss elimination, what's the reduction, right? So you start from the matrix A here, you know that eventually you will reduce to this matrix. So let me just copy down here. So we already have the REF. So so this is the A we start with, right? And from earlier part, we can reduce to the REF like this. -1. So you can see that I'm kind of recycling what I already did earlier, right? So now this is your REF. And this is actually a review for column space, right? So we want to know which columns are linear independent, right? So the pivot is in this first and second column. So we know the column 1 and column 2 of A are linear independent, right? So those are my bases. So basically, then I can just say the range of L, which is everything, right? The column space. This is nothing else but the span of the first column and second column. And remember that to be safe, we should always use when you write down the basis for the column space, you should always use the original column, right? Because we only know the linear independency are the same for REF and the original A, but the column space may look different. So when you're trying to pick up the correct basis for the column space, you should pick up the original column. So this is essentially span of the first column and second column. But if you notice that this is actually a 2-dimensional subspace in R2, right? So this is essentially should be if you want to be really precise, you will see that span of these two vectors should be the whole R2. And this is our image. And or you can actually tell me that the basis is these two vectors, right? Depends on how you want to express it. Either you can tell me the information about the basis, or you can rewrite it in a span of something. Okay. Any questions so far for this part? Okay, so this is part B. Okay, and part C, as you can imagine, at some point I'm definitely going to ask this question, right? So I have two bases, right? This is in R3. The U is in R3, and the V is in R2. So essentially, I give you two set of bases, and they're all non-standard, right? So one is the basis for R3, and one is the basis for R2. That's in the image. And I said that, okay, then I want to find the matrix representation for this linear map that I will copy down the definition in a minute. But I want to find a matrix representation with respect to this new basis U and V, right? One in the domain and one in the image, right? So this is not standard anymore. So of course you can imagine it's not going to be the same as our matrix A. So first, let me recall what's the definition of what's the formula for finding this matrix representation, right? Let's call it B just to distinguish from the first case. So essentially, the matrix B you are looking for looks very similar to the standard case. So you still need to plug in, no matter what, you should always plug in the basis you're going to use from domain, right? So in other words, you need to still plug in L of U1, L of U2, and L of U3, right? You need to use the basis because all we care is how the map acting on the basis. But we need to do a little bit more because we're using a non-standard basis. So we need to do some kind of change of basis. So your first column is not just L of U1, but it's the coordinate of this vector with respect to the basis V. Right, so that would give you the, so first you find L of U1, right? So if you want to do it step by step, for example, you can first find L of U1, and then you will have a vector. Whatever that vector is, you need to find the coordinate of this vector with respect to this new basis V. But of course, as you can imagine, if you want to do step by step like this, it's actually taking too long, right? Because you need to do a lot of change of basis. And as you can imagine, because you have 3 columns, you need to do 3 times. So it turns out that if you still remember back in 4.2, we actually have a nice scheme that we can put everything all and solve it all at once, right? So there's a scheme here that we can do. So I'm not going to re-explain it because I'm not going to reteach it again. This is from 4.2. So you can actually check the lecture notes that we did when we covered the 4.2. But I'm just going to tell you the scheme here. So basically what you can do is I'm just kind of put the change of coordinate in like 3 times of change of coordinate all in once, right? So the scheme can be reduced to the following. So you have this new basis V, right? So you put a V here, right? And the right-hand side is really just L of U1, L of U2 without changing anything, right? You have 3 columns here. And what you want to solve is you want to first put this like this, right? So on the left-hand side, you have the basis V. Right-hand side, you still need to find out what L of U1, L of U2, L of U3 is. But then what you want to do is you want to do the reduction, right? So we want to do reduction such that the left-hand side will become the identity. And whatever the right-hand side left is the matrix you are looking for, right? So just to give you a little bit review why this is the correct scheme and why this is the case, right? So if you think about it, what we really want to solve here is L of U1, but in terms of the coordinate of L of U1 in terms of the basis V, right? So if you want to do the change of coordinate, what would it look like, right? Then you essentially, let me just recall, right? So essentially what we did is really you take V, the basis V, right, times L of U1 with, this is the unknown, right? This is the we want to solve, right? And equals the standard basis, right? If we want to do the change of coordinate, but the standard basis is E, right? Which is actually identity, so I can omit it. And the right-hand side is identity times L of, say, U1, right? With respect to the identity or the standard basis, but that's essentially just the L of U1 without anything. So you can see that if you want to solve this change of coordinate here, what you really solve is a system of equation, which looks like V times the unknown equals the right-hand side, right? And this is exactly what we were doing. V times unknown equals this, right? When we're trying to solve a system. But instead of solving V times unknown equals L of U1 and do it again for L of U2 and do it again for L of U3, what we did here is put it all together and solving a giant augmented matrix, right? So you can actually solve, in some sense, I'm solving 3 systems all in once. That's why I put it like this. And then eventually you want to solve everything, right? And you should be able to solve it because V is like invertible matrix. So you should be able to reduce to identity. So that's just a quick review here. So now let's see. So as I said, I need to recall the definition for L. Otherwise, it will be very puzzled. So I'm not going to go back to refer. So L of X is actually X1 plus X2 and X1 minus X3. So that's what we have from very long time ago. Okay. So now the only thing we need to do at this for now, before we start solving, is I need to find out L of U1, L of U2, L of U3. Okay. So now let's see. So L of U1 is, okay. So let's go back. 1, 0, minus 1. So you just have to believe me for now, because then otherwise I need to go roll back and forth. Okay, so I also need L of U2. Let me just write down everything here. Okay, so I need this 3 column, right, before I can solve the system. Okay, so now let's just use the definition, right? So we have 1, 0, minus 1. So this would be 1 plus 0, 1 minus 1. So this would be 1 and 2. Second one would be 1 plus 2 here and 1 minus 1. So this would be 3, 0. And we have minus 1 plus 1, minus 1. So this would be 2 minus 2. Okay. So now, once you have L of U1, L of U2, L of U3, we're plugging into the right-hand side, right? And the left-hand side, that's V. We already have it, right? And then, so you can see that this part you definitely need a little bit more work, right? So you need to first find L of U1 to L of U3. Then you need to solve this giant like augmented matrix. So that, let me put V here. And be careful when you put V here, this is V1. This is V2, right? When you're trying to turn it, when you're trying to treat everything as a basis, please put it as a column vector, right? So let me go back to C, right? You can see that all the things U1, U2, and U3, I'm written out as a column vector, right? So when you're trying to solve some augmented matrix, most of the time, you should put it as a column vector. So the V1, V2 is 1 minus 1 and 2 minus 1 here. So that's V, right? And the right-hand side is the L of U1, L of U2, L of U3, okay? So now we really need to solve it, right? Do the Gaussian elimination, okay? So first, let's see. So I'm going to take this one and add it here. So that would be 0, 1. Okay. I know I'm doing very fast here because I already kind of know the answer. So when you do the computation, please just slow down so you don't make the mistake here. Okay, so now let's see. So I want to solve to identity, right? So I still need to take this 1 and then cancel out this 2. So let's see. So this will be, now it's done. So we'll have. Okay, so not too bad. We only need 2 steps, right? So you can see that after 2 steps, Gaussian elimination, right? So the left-hand side here is identity. And as I said, right-hand side would be your matrix representation that you're looking for. Okay. So definitely there's some other way to solve this type of problem. But to me, this is more systematic way. So you don't mess up things. But when you're trying to, if you are using something non-standard method, right, please give me some explanation. This is something I saw in the past that a lot of people would just give me like a whole bunch of number and equation and without explanation what they're doing, right? And then the calculation is all over the place. Then it's very hard for me to follow, and I really don't know what like where the word come from, right? So not only you need to provide enough calculation, right? And then also you need to provide a little bit explanation what you were doing, right? Like for example, you cannot just come up with some column and then plug in from nowhere, right? Then I don't know where the number come from. Even though sometimes I know that the calculation or things might look straightforward, but you need to give me enough like explanation, right? Like when I grade the exam, I will assume that I don't know the answer at the first place, right? Like I'm like your peer that I don't know what's going on. So you need to convince me by using the correct logic and enough argument that to convince me that from step to step, that's enough to lead to your answer, right? So that's the way I would grade the exam. Okay, so this is B, right? So that's for part C. The last one is actually similar to one of the homework problem, I think, in section 4.2, I believe. But this one, it's actually kind of tricky in the sense that there's several ways to solve it. But it's actually, if you can find the part C already, you can directly use the answer from part C. That's the beauty of this. So the fourth question is, if you have a vector from the domain, and I know this vector can be written as the basis U1, U2, and U3 we just found as a linear combination. Now the question is, if you plug in this X vector, right? Maybe I should call this some other name to, I don't know, maybe let's call it, I don't know, W, right? I don't want to confuse with general X, so let's call it W, that's better. So I have this vector W, and W equals 2U1 plus U2 minus U3. And I want to say, okay, can I express L of W as a linear combination of the bases V1 and V2, which is given from part C? So of course you can say, okay, I'm just really first, I mean, one way to do it, which is maybe more detour, is say you really found U1, you plug in U1, U2, U3, found literally what W looks like, and plugging into L and then solve the linear combination. Of course, you can do that, but that would take a while, right? Because you need to really solve for W, solve for L of W, and solve for the linear combination. That's okay, but it's much longer, and you could possibly make mistakes. One shortcut here is the following. So first of all, we realize that if W can be written as linear combination like this, that means if I'm asking for the coordinate of this vector with respect to the basis U, this means that you have the coordinate of this vector 2, 1, minus 1 with respect to the basis U. And why we care so much about this matrix B in the part C, right? Remember what B is. B is the matrix representation of the linear transformation with respect to the new basis we have, right? So that means the significance of this matrix is following. That means if you are looking for the output, right? If you want your, whatever the output you have, L of X or L of W, doesn't matter. If you want your output to be represented in terms of the new basis V, it should be the same as this matrix you found times the entry, the input X, but in terms of the basis U. So this means that because we already found this matrix representation B, and this B is with respect to the new basis. So this basically tells you if you plug in an input vector, which is already in terms of the new basis U, then the output, whatever the vector you found, would be the output L of X, but with respect to the basis B. That's essentially the meaning of this matrix B, right? So this means now you can see that we already know the coordinate of W with respect to basis U is 2, 1, minus 1. If we multiply by this B, then the output should be automatically the coordinate of L of W with respect to basis B. That's essentially the beauty of this matrix B and the most significant use, right? Because everything is set up in the right way because we already found B in terms of the correct appropriate basis. So everything should match up correspondingly. So now the only thing we need to do is, okay, then we know, because if you ask what would be L of W as a linear combination of the basis V, then you're actually asking similar question. You're looking for the coordinate of this vector with respect to basis V, right? So what we want to do is really take the B times the coordinate of W with respect to U, right? So I just do one matrix multiplication, so you can see that this will be the case. So this basically tells me, okay, that gives me the coordinate of alpha W with respect to basis V. So, but then I'm asking for linear combination, right? So you just rewrite it as -7 V1, sorry, and plus 11 V2. So you can see that if you know what B is really for, then this problem is actually, I would say, 2 minutes, right? Instead of really solving for everything from scratch, okay? Because when you solve everything from scratch, in some sense, you're actually repeating the process of part C. Okay, so any question so far for this big part? So you can see that this is actually all the key things that we mentioned in chapter 4 and maybe a little bit earlier things, right? All together. So this is like a more conceptual type of question. Okay, so then for chapter 5, we didn't do much, but we actually hit several important things. First, we do some kind of scalar product projection, and we also do the orthogonal subspace, right? So basically, just quickly review. So if you say that two vectors are orthogonal to each other, that means the scalar product, or you can say the dot product, is actually equal to 0. That's the immediate way we can check. And we also know about that if you want to find the length, it's the square root of the dot product with itself, right? And we also know that the angle between two vectors, right? Or if you say the cosine of this angle between two vectors is related to the scalar product in this sense, right? And even more, like the one key thing we did is that we actually use the scalar product to do the vector projection, right? So be careful, it depends on which vector you want to project onto which one, right? The order matters. So if you want to do vector projection from X onto V, right, then the picture is the following, that you essentially, you have a vector X, right? You want to project things onto Y, for example, then the resulting projection vector will be along the same line as Y. And this is the formula we derived last time when we talked about 5.1, right? So be careful the formula here, right? I mean, I think this is open book. So if you really forget about the formula, just quickly check, right? You can use your notes or your textbook. Just don't mess up the formula here. And after you do the vector projection, then this projection vector, if we call it P, will be parallel to Y in the sense that it will be along the same line as Y. But then if you do the subtraction, meaning if you do the subtraction of X, minus P, then this vector, we call it Z, will actually be automatically perpendicular to Y. And this is what we call the orthogonal decomposition, right? So by using this type of projection, you can actually decompose a vector into two vectors which are mutually perpendicular to each other, right? So this is what we call the orthogonal decomposition. And this can be very useful in a lot of subjects. Okay, so now let's see this example, right? So I want to say, okay, write this vector X as a summation of two vectors U and V, where U is in the same direction as this vector Y, and then V is orthogonal to Y. So this is really just a rephrase of what we said about the orthogonal decomposition. And here, please be careful, right? Like I use X and Y in here, but do not always blindly remember the formula for X and Y. For example, I could possibly just change the notation, right? I can say, write U as a sum of V plus W, or I can change the notation, right? So you need to remember the concept behind the problem, not just the notation, okay? So now let's see. So we have, we want to do this orthogonal, right, decomposition. So if you want to write, the picture will be pretty much the same here, right? So P here, actually the U, sorry, because now I say U. So let me actually rewrite the picture so everything is in the right notation. So I want to do the projection here, right? So the projection is U, and the vertical one is V, okay? So now U is the projection vector projection of X onto Y, right? So by the formula here, we have the dot product, right? And the formula is top here, divide by the square of the norm, right? And this number times the vector Y, right? So now let's see. So I have the numerator is dot product. So I have 2 times minus 1 plus 10. That's 5 times minus 5 times minus 2 and plus 4. And divide by the square of the length. So this will be 1 squared plus minus 2 squared plus 1 squared. Actually squared, so I don't need this. Okay, this whole thing times the vector Y. Okay, that's not too bad. So I have 14 minus 2, that's 12. 1 plus 4, 5, that's 6. So this is 2. So 2 times that, this would be minus 2, minus 4, and 2. Okay. So this is the vector U, right? So what would be V, right? V, essentially, we can see that once you found the correct projection, right? You need to first find the correct projection. Then V, because you want the decomposition to be true, so V is really just X minus the projection you just found, right? So VU is actually a bit more work. So X would be 2 minus 5 and 4 minus U, right? So this would be 4 minus 1 and 2, right? So this will be V. So now let's double check our works, right? So X should be able to be written as U plus V, which is minus 2 minus 4 and 2 plus 4 minus 1 and 2. That's double check, right? And this should be the same as 2 minus 5 and 4. Yep. And what last checking you can do here is the following, right? Because at least you can eyeball the answer that they add up to be X. But another thing you should check is actually that you want to check that U is really perpendicular or orthogonal to V, right? This is actually what we really want, right? So because first of all, U is already in the direction of, it's a multiple of Y, right? So that's fine. But we want to check the orthogonal part, right? So let's check the scalar product of U and V, right? So this would be minus 2 times 4. That's, let me just directly do it. So minus 8 plus 4 plus 4. Yeah, this is really 0. So you want to double check that when after you found the claimed decomposition, orthogonal decomposition, you want to make sure that those two vectors really perpendicular to each other, right? Because if you messed up any step, it's possible you can still find the correct decomposition, right? You could have decomposed in a bad way. Maybe like you decompose a vector like this, right? It will still be, the sum will still be correct, but they are not perpendicular anymore. So you need to actually check both the sum is correct and also they're perpendicular.
I think I'm a little confused on your equation there, because you've got the magnitude of the vector Y squared in the denominator.
Yeah.
But when you did your, when you actually created the equation there, you dropped the square. Is it actually the square of the magnitude or just the magnitude?
So what's the magnitude of a vector? Magnitude always carry this. The magnitude is actually carry a square root, right? This is the magnitude, right? When you calculate the length of a vector, right? Remember, length is essentially from the distance from origin to whatever the point is, right? So, right, yeah, you always carry a square root, yeah, and then you squared it, right? Yeah, so that's why. So yeah, so be careful here, like we are actually doing the square. So I mean, it should be more or less easy, right? Like in some sense, you don't see the nasty square root anymore. Okay, so now this is not too bad. So from now on, this a little bit more conceptual. So let's see. So Now we move to 5.2, where we talk about orthogonal spaces and also in particular the orthogonal complement. So let's review a little bit definition here. So we say two subspace X and Y are called orthogonal to each other. And this is a little bit stronger because we are now talking about two collection of vectors, right? So what that means is that you need to check the scalar product between any vector, every vector coming from the vector space X, and then also with any vector from the vector space Y. So if any such X scalar product with Y is 0 for all such X and Y, then we say these two spaces are orthogonal to each other. Okay. And we also talk about a spatial subspace called orthogonal complement. So you give me X to be some subspace in Rn, for example, then what's orthogonal complement? Orthogonal complement means that it's the collection of all the vectors out there such that it's going to be orthogonal to every vector in X, right? So we actually see this example before. So unfortunately, I can only draw the three-dimensional picture. But let's say if I want to say what would be if I'm just made up some example here. So if my say X is this space, right? If the X is span of 1, 0, 0, okay, right? Span of E1, what would be the orthogonal complement? You want to collect all possible vectors out there such that it's going to be perpendicular to any vector on this red line. Then you can imagine it's actually, because it's complement, right? So your X is one-dimensional. So if you're in R3, your complement should be a two-dimensional subspace. So as you can imagine, the subspace we are going to have, the complement should be the XY plane. Oh, sorry, YZ plane, right? Because everything lies on the YZ plane should be any vector which lies on this YZ plane should be perpendicular to any vectors on the x-axis, right? So you can see that YZ plane is two-dimensional and x-axis is one-dimensional. So they actually add up to be the ambient space, the 3, right? So this is a geometric picture that to help you to see that what the orthogonal complement looks like. So this would be the orthogonal complement if my X is the span of E1. But of course, I can easily draw it because it's the example I made up here. The picture is quite trivial because I picked the nice explicit lines, so everything looks nicely. I can easily sketch it. But what if for example, I'm in higher dimension, or maybe it's not really just x-axis anymore, right? It might be some tilted line. Then it might be a little bit harder for me to explicitly draw the picture or actually to find the basis of the orthogonal complement. So it turns out that if you already started or almost finished the homework problem, you should be able to see what do you mean? Repeat which part? The last part? You mean this orthogonal complement or the vector projection? Oh, representation. So the thing is that I'm looking for the orthogonal complement. So I pick an example, right? I call the subspace X to be span of E1, right? So it's a one-dimensional subspace, which is essentially the entire x-axis. So I want to find the orthogonal complement for this x-axis. So the definition for orthogonal complement means that it's every vector out there such that it's going to be perpendicular to anything on this line. But I need to collect every possible such vector. So you can see that any possible vector out there which is going to be perpendicular to x-axis is everything on the YZ plane, right? If it's not on the YZ plane, it's not going to be orthogonal to x-axis, right? So I collect all the possible vector which is on the YZ plane, right? So then essentially it's an infinite large plane. I cannot draw it, but that's why I just say it's a YZ plane, right? And the YZ plane is perpendicular to x-axis, right? If you look at my image in the camera, right? So I have a YZ plane, which is the wall, right? And I have my x-axis. So every vector on the YZ plane should be perpendicular to x-axis, right? So this collection, the O vector on the YZ plane, right? So essentially my YZ plane is the complement because I'm collecting all the possible vector out there, which is perpendicular to anything on X in this case, right? Yeah, but of course, if you can imagine, if I change the subspace X, then the picture will change, right? For example, if it's not X axis anymore, if I tilt it, if I choose different X, for example, then the plane should be corresponding like tilted, right? That's why I said that in general, it will, if it's a general example, it will be hard for me to draw the correct picture. So then, but at least in the homework problem, I want to do one similar homework problem like this, that it will help you to at least solve it directly using the algebra here. Because for example, as you can see in this example, it's not in R3 anymore, it's in R4. So I cannot really draw the picture. So, but still I can solve it in terms of the algebra here. So using some knowledge we already know before. So let's say in R4, now my ambient space is R4. S is a subspace, which is the subspace spanned by these two vectors in R4. And I say, okay, I want to find the basis for my orthogonal complement for this vector space. So first, before we solve it, you should ask yourself, how many vectors are we going to expect, which would be the basis for complement? So I have R4, right? And my space S already have 2 dimension, right? So first, my subspace S is the span of X1 and X2. So you can imagine this would be a 2-dimensional subspace, right? So can anyone want to answer this question? If I know my S is 2-dimensional subspace, it lies in R4, what would be the dimension for my orthogonal complement? Does anyone want to give me an answer?
Would be 2.
Would be 2, right? Because it's complement. That's why it called complement, right? So you should expect that the dimension of the orthogonal complement should be 2, meaning later on when you find the basis, it should have 2 vectors, right? As a basis, right? If you find more than 2 or less than 2, that's something is wrong. So now I need to see what the original subspace looks like. It's the span of X1 and X2, which means that it's every vector in the form. So I'm collecting all vectors. Let's call it X in the form as because the span of these 2, right? So it will look like a linear combination of X1, X2, right? These 2 vectors. Okay. So now if we want to find the orthogonal complement, right? Then that means you want to collect all the possible vector, say Y, out there, such that it's going to be perpendicular to every X like this, right? So we want to find a vector, every vector in the orthogonal complement, right? Such that Y is perpendicular to X for all X from the subspace, right? It needs to be orthogonal to every single X like this, right? But if you think about it, since my vector X always looks like linear combination of this one, X1 and X2. So I don't need to check every single X. All I really need, the logic here is that all I really need is to make sure this vector Y is orthogonal to my basis, X1, X2. If that's the case, then when you do the scalar product, this C1 and C2 is not going to affect the fact that it's going to be orthogonal. So all I really need to do, so it actually, the upshot is, it's suffice to solve that Y is perpendicular to X1 and Y is perpendicular to X2. That's it. If these 2 are satisfied, then Y will automatically be perpendicular to the linear combination of the bases. This is, I think, one of the homework problem. I forgot which number. It's among number 2, 3, and 4, one of them in section 5.2. I think I assigned either 1 or 2 problem like this. You probably already did it, so you already have some sense about it. So if we want to solve this, then that means all I really want is to solve the scalar product to be 0 for both of them, right? So I want scalar product to be 0 here, and I also want the scalar product of X2 and y to be 0. So now let's put it in terms of the explicit format. So I want to do the scalar product. So that means one of them, I want to turn it into the horizontal vector, right? So actually x1 would be 1, 2, minus 1, and 1. I want to do the scalar product with y. So I'm solving for y. Right, so y is unknown, but I want this to be 0, right? And also I want x2 scalar product with y1, y2, y4, that's y to be 0, right? So I'm solving these two equations. I put it explicitly in explicitly every coordinate. Now, if you think about it, this is nothing else if I just leave x1 as it is, right, and x2 as a horizontal. What you are really solving is the null space, right? So because if you call A to be this matrix, which means that this time is a bit spatial. You're putting x1 and x2 as row vector, right? And essentially you are solving A times y, right? So then essentially, let me put it all together. So we want to solve y such that y is in the null space of A, right? This is essentially what it turns into. If you want to solve any vector y from the orthogonal complement, it's the same as solving y to be perpendicular to each row vector. And if you put these two vectors, right, the basis one into the row vector of A, then in other words, if you want to solve orthogonal complement, it becomes solving the null space of this matrix. But be careful, this is very different than back then because now we put things in the row vector. I think this is the only time we actually put basis into row vector. Okay, so you probably already saw that in the homework. So now all we really need to do is to solve the null space of A. So essentially in this case, I should say the null space of A is the same as orthogonal complement. So I just need to find the basis for my null space. Okay, so now let's see. So I'm going to just do a quick row reduction. Okay, so give me a second. So I'm showing you some process, so later on you can compare with my thing. Okay, so this should give you the REF. Okay, so now let's see. So we have two pivots here. So let's see. So I have x4. Oh, actually, let me call it y4. Y4 to be beta, and y2 is alpha. That's the two free variable. And my y3 is minus 2y4. That's minus 2 beta. And y1. Okay. So y1 is minus 2 y2 minus 3 y4. So this is minus 2 alpha minus 3 y4. Sorry, beta. So this y should looks like y1, y2, y3, and y4. So the two vectors as basis. So let me factor out alpha. So that's minus 2, 1, 0, 0 plus beta minus 3, 0, minus 2, 1. Right? So the basis essentially is these two vectors. So these are the basis for the orthogonal complement, right? So this is, if you haven't done the homework, then this should help you to do as I said, right, the homework 2, 3, and 4. I forgot which two I assigned, but this essentially is the whole concept for and then I think one of the homework, maybe 2 or 3, one of them actually also explained what I was doing there using like part A and B and C and trying to lead you through the whole process. So you're going to see similar thing over there. So when you do the homework, just keep eyes on these three problems. Okay, so then there's another more conceptual question that this is actually, we also discussed this in 5.2, which I also want to mention it. So if you have a matrix A, right, we just mentioned that this notation R of A is range of A. And we actually did an example, like I think in chapter, just the first example we did, we mentioned range of A is essentially the column space of A, okay? And if you check, it turns out that we have this fundamental subspace theorem tells us the range of A transpose is the orthogonal complement to null space of A, or vice versa, right? Orthogonal complement is a mutual concept. And if you swap the role of A and A transpose, then you will have the same thing. You can also say that the range of A is orthogonal complement for null space of A transpose. Okay, so you be careful, right? Here, one of them is A transpose, the other is A, right? So if they're orthogonal complement to each other, then of course they're going to be orthogonal to each other. Okay, so then this one question, I think maybe I think it's in the homework problem. I think I assigned this, but since it's almost the end of the semester, I would just want to go over this problem. So the question is asking, is it possible that you have a matrix which has 3, 1, 2 in its row space, meaning it's in one of the row or in row space, right? And or as a linear combination of the rows, and at the same time having 2, 1, 1 in its null space of A, right? So of course, like if you don't have the concept about the fundamental subspace theorem, then this problem seems random, right? How do you know whether I could have possibly have such metrics, right? And especially you don't have the explicit example for the metrics. So it turns out this is very conceptual. So what we really need to do is really to use the concept above. So first of all, let's see if we want 3, 1, 2 to be row space of A. This means if you transpose, right, like flip the row to column, then this means this vector 3, 1, 2 should be in column space of A transpose, right? Because the things in the row space of A should be in column space of A transpose, right? Then if it's in the column space of A transpose, right? So the row space of A should be the same as column space of A transpose, right? You just turn the row into column when you flip the matrix. So if this is the case, that means you just use the notation, right? Then it means that this 3, 1, 2 should be in the range of A transpose. Okay, let's put it here for a while. But now we also want the other vector 2, 1, 1 to be in the null space of A transpose. Null space of A, right? So now you're telling me I have one vector 3, 1, 2 in the range of A transpose, the other vector 2, 1, 1 in null space of A. What do we know about this two space? We just said they're orthogonal complement to each other, right? The first one. Null space of A should be orthogonal complement of range of A transpose. That means they're mutually orthogonal, right? So we know since null space of A is orthogonal to range of A transpose, so any vector from this space, null space of A, is perpendicular or orthogonal to any vector from the other space, right? This is what essentially the definition of being orthogonal. So now what we really do is, okay, if that's the case, let's do the scalar product and see whether this could possibly be true, right? So, but then you check, you take, either one of them, right? You take 2, 1, 1 scalar product with 3, 1, 2. As you can see, they're all positive, right? So there's no way it's going to be 0, right? So basically that tells you it violates or contradicts to what we know about the two space to be orthogonal. That's why it's impossible. So not orthogonal, right? So it's impossible to have such matrix, because once you find out that what each vector we want it to belong, it turns out that it doesn't really match with what we know theoretically. So this is actually a very conceptual problem. Seems easy or seems random, but it's actually essentially tests you whether you understand that these two spaces are also gonal. Okay, so hopefully that will also help. Like, I think I assigned one of the homework like this. Okay, last question regarding this type of thing is another one like this. Also not bad at all, but it's also conceptual. Once you know the idea, it's actually really, I would say, 2 lines or even 1 line. So if you have a 7x5 matrix with rank 3, so what's rank? Rank is the dimension of row space. That's the definition. Okay. If you know the rank is 3, what is the dimension of null space of A transpose? Okay. We can ask this question without even explicitly know what A looks like. Okay. So now let's see. So first, what we should know is that in order to connect rank with null space, you need to remember this rank nullity theorem, right? So I'm also trying to recall something that we learned a long time ago. Rank nullity theorem, right? And this time, because I'm asking for null space, the dimension of null space on matrix A transpose. So I need to do this theorem on the A transpose, right? So essentially, this theorem tells us the rank of whatever matrix, in this case, I want the transpose, plus nullity of A transpose, right, is equal to the right-hand side is the number of columns of the matrix. Okay. So what's nullity? Nullity is essentially what we were looking for, right? This is the dimension of null space of A transpose. So now you need to find out the other 2 information, right? And do the subtraction. So the right-hand side is easy, right? Because we know A is 7x5. That means A transpose is the other way around, 5x7, right? That means you have 7 columns for A transpose, right? So the right-hand side is just literally how many columns are there, okay, for A transpose. So you need to flip it. Now the question is, what would be the rank of A transpose, right? What we have here, 3, is the rank of the matrix A. But it turns out that we can use what we knew before, the knowledge, to find out the rank of A transpose. And surprisingly, not surprisingly, they're the same thing. So the reason is the following, right? So you have the rank, which is the dimension. So rank of A, right? This is 3, is the dimension of row space of A, right? But we know that by something like the theorem earlier, the dimension of row space is the same as dimension of column space. They should have, because they all corresponding to how many pivots are there in the end in the REF, right? But what's the column space of A? Column space is essentially row space of the A transpose, right? And now you got the row space of A transpose. The dimension of row space is the same as rank. So essentially, it tells me rank of A should always be the same as rank of A transpose. So then you have 3 here, right? So then the thing you want, the dimension of null space of A transpose is really 7 minus 3, which is 4. Okay. So you need to really know, like first you need to recall the rank nullity theorem. Then you need to know which entry you should plug in, right? Because there are so many numbers here, right? 7, 5, 3, which one you should plug in, right? You should really know that what does it mean for each entry, which entry you should plug in. Okay, so this shouldn't be too hard. I mean, I'm writing down a lot of detail, but this is actually very explicit and really just simply by the rank nullity theorem. You just need to know like what's the rank of A transpose, and you need to remember to flip because I'm asking for the columns of A transpose. Okay, so then for 6.1, I don't want to do the review anymore because like we just do the 6.1, like the eigenvalue. So for the eigenvalue, as I mentioned, you only need to check only need to know the real eigenvalue. So I would suggest you need to know exactly what to do on the homework problem. That's it. And then also the example I mentioned in the class. If you can do that, then I think you'll be fine, right? Like either 2 by 2 or 3 by 3, like or 2 by 2 or 3 by 3 eigenvalue problem. Okay, so we only have a little bit limited time, so I want to at least go to the next question here, which is essentially find the basis for, this is something that we learned in 3.6. But I mean, I bet right now at this point, because we have seen so many null space, column space, and row space. So I'm just going to do very quick just to make sure that everyone understand the concept. So I put it all together, right? Row space, column space, and null space, right? So at this point, you should realize that the only thing you really need to do is reduce this A to REF. That's it, right? And then once you reduce to REF, right away you can see at least you need to solve for null space, that's for sure. But for column space and row space, you can right away see what would be the basis, right? After you get the REF. So I'm going to, I mean, I don't have time, so I'm going to like leave as exercise for you to figure out the middle step. But I'm going to tell you what's the REF for this problem. So this would be the REF you're going to see. Right? So you have 3 pivots here. Okay. So now if you have 3 pivots here, right, then we can right away, just by this REF, we can right away identify what will be the basis we are going to use for row space, and also which columns will be the independent one that we're going to use as a basis for column space. That's pretty much immediate, right? So basically, the basis for row space of A, right? Essentially, because the first row, second row, and third row has the pivot. So you can pick out the first 3 rows, right? Those are the independent one. So there are 3 rows here. And since row space of A is exactly the same as row space of this REF, if you code it U, so it really doesn't matter for row space that which rows you use. You can use the rows coming from U. You can use the original rows. It doesn't matter. So I can just use the simple one, like the one coming from U. So I have 1, -2, 1, 1, 2, and 0, 1, 1, 3, 0, and 0, 0, 0, 1. So these are the 3 bases I have, 3 vectors, right? And as you can see, I put it in the row vector because it's the basis for row space, okay? So, and then if you want the extra information, then at this point, you can tell me the rank is 3 because you have 3 pivots here. And for column space, it's also immediate. So the basis for column space, right? Because now we look for independent columns. So this tells me first, second, and last one will be the independent one, right? So from REF, we know A1, right? A2 and A5 are the basis, are linear independent. That's the basis, right? So the column space, the basis is first, second, and fifth column. But this time, for column space, you need to use the original column. So you have this 3, right? So it will be 1, -0, 1, -2, 3, 1, 2, and 2, -2, 4, 5. Right? These are the original columns of A, right? So be careful here, right? For column space, you need to use the original column. So now for the null space, unfortunately, you need to really solve it, right? But this is not too bad. So let me just copy down let me copy down the matrix here, the REF. So since you already have REF, you can right away solve for the null space, right? So this shouldn't be too bad because you have been seeing so many this, right? So you have right away you can see we have 3 pivots. So x3 and x4 will be the new the free variable. And x5 here is right away 0, as you can see. And x2 is minus x3 minus 3x4. And x1 is 2x2, right? And 2x2, yeah, minus x3 minus x4 minus 2x5. Okay, I'm going to skip a step because I'm running out of time. I'm just going to tell you the answer in the end. So we can solve the system. The solution would be something like this. X2 would be minus 3 alpha minus 3 beta, x3, x4, and 0. Okay. So you actually have 2 bases here. Oh, sorry, it's minus alpha here. Yeah. Minus 1, 1, 0, 0, plus beta, minus 7, minus 3, 0, 1, 0. Okay, so you have to actually have bases for 2 bases. So these 2 vectors will be your bases. And you can see that this makes sense, right? Like your dimension of the nullity, essentially, dimension of null space is 2, which plus the rank is 3. So it consists of 5 columns. Okay. So so unfortunately, I still have several questions afterwards. I have maybe 1 or 2. So don't forget that to read my review notes. So I will provide the detailed solution after today's class. So all the problems that I couldn't touch, I will put the detailed solution there. So you can actually like see the solution. And then if you have any question, please let me know. Right. So, but essentially, I think I go through several important things, at least from chapter 4, 5, and a little bit from chapter 3.6. And there are other things from the older material. What you should do is to go over the exam 1 and exam 2, right? If you have any mistakes from those 2 exams, you should definitely know how to do those problems. I will focus on similar type of problems from exam 1 and exam 2. Okay. So I will announce the office hour for next week. And as I said, if you cannot make it or if you have any question over the weekend, feel free to email me. Okay, so sorry for a little bit over time. So feel free to go if you don't have any questions.
Will you be having an office hour tomorrow or no?
No, but if you have any question or if you want to make an appointment with me, that's fine as well. You can maybe email me the questions, or if you want to talk, then we can set up appointment. It's up to you.
Okay.
Yeah.
Thank you.
Yeah, welcome.